You know that the p block elements are placed to the right side of the periodic table in groups 13 to 18. You also know that in the atoms of p block elements, the differentiating electron enters the valence p subshell. Thus, in these elements, the NP subshell is gradually filled. On account of this, the general valence shell electronic configuration of these elements is NS2, NP1 to 6. Note that the electronic configuration of helium is 1s2. Although helium does not have p orbitals, it is a p block element because it resembles that of other p block elements of the 18th group with respect to their properties. Most p block elements are non-metals, while the remaining are metals and metalloids. Thus, the presence of all the three types of elements in p block of the long form of periodic table bring diversification in chemical behavior of these elements. The study of these elements is an important area in chemistry, as these elements and their compounds have immense significance in industries and day-to-day life. Now let us turn to the study of group 15 elements. Let's first discuss the occurrence of these elements. The elements in group 15 are nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen is the major constituent of the Earth's atmosphere and accounts for 78% of it by volume. It is the first member of this group and occurs in free state as a diatomic gas, N2. No other element of this group exists in free state. In combined state, it mainly occurs in the form of minerals such as Chile salt Petri and Indian salt Petri. It is also found as the essential constituent in proteins, amino acids, nucleic acids, and enzymes. The next element in the group is phosphorus. It is the 11th most abundant element in the Earth's crust. Being a very reactive element, it does not occur in free state in nature. In combined state, it occurs in the form of minerals as phosphates. Chloropatite, fluorapatite, and hydroxyapatite are some examples of phosphates. These comprise the apatite family. Phosphorus is an essential constituent of plant and animal matter. Phosphate groups are among the important constituents of nucleic acids, that is, DNA and RNA. About 60% of bones and teeth are composed of phosphates. Phosphoproteins are present in egg yolk, bone marrow, and milk. The remaining elements of the group, that is arsenic, antimony, and bismuth, mainly occur as sulfides. For example, arsenopyrite, stibnite, and bismuth glands. Now let's look at the electronic configuration of group 15 elements. The differentiating electron in these elements enters the NP subshell. Hence, the valence shell electronic configuration of these elements is NS2NP3. So, it is evident that these elements have 5 electrons in their valence shell. The electronic configurations of these elements are listed in the table here. Due to the exactly half-filled electronic configuration of the NP subshell, the elements of this group are fairly stable. For example, dinitrogen is an inert gas under normal conditions. Now, let's look at the trends of some atomic properties of group 15 elements, such as atomic and ionic radii, ionization enthalpy, and electronegativity. A comparison of these two tables shows that as we move down the group, the atomic radii, covalent radii, and ionic radii increase due to the addition of a new principal energy level in each successive element. There is a considerable increase in the covalent radius from nitrogen to phosphorus. This is due to the effective shielding of the s and p electrons present in the penultimate shell of phosphorus. However, from arsenic to bismuth, there is only a small increase in the covalent radius due to the poor shielding effect of the d electrons of the penultimate shell in arsenic and antimony, and the poor shielding effect of the f electrons of the antipenultimate shell in bismuth. As a consequence, the effective nuclear charge increases, which leads to a small increase in the covalent radius from arsenic to bismuth. Now let's look at ionization enthalpy. Group 15 elements show higher values of ionization enthalpy as compared to group 14 elements. This is due to their higher nuclear charge, smaller atomic radii, and stable half-filled electronic configurations. However, as we move down the group, the value of ionization enthalpy decreases. This is due to the gradual increase in the atomic size, which reduces the force of attraction between the valence electrons and the nucleus. Finally, let's look at electronegativity. You know that electronegativity is the tendency of an atom to attract a shared pair of electrons more towards itself. The values of electronegativity of these elements are listed in the table here. As you can see from the table, the electronegativity decreases gradually on moving down the group from nitrogen to bismuth, due to the corresponding increase in the atomic radii. Note that after fluorine and oxygen, nitrogen has the highest electronegativity. Let's first study the physical properties of group 15 elements. Physical properties include physical state, metallic character, melting and boiling points, density, and allotropy. Let us look at each in turn. Nitrogen is a diatomic gas, while the remaining elements are solids. You know that as you move down a group, metallic character increases. The same trend is observed for group 15 elements too. Do you know the reason? Try to answer this question on your own before looking at the answer. As you move down the group, the ionization enthalpy of the elements decreases with an increase in their atomic size. In other words, the effective nuclear force of attraction on the valence electrons decreases down the group. As a consequence, the metallic character increases down the group. The first two elements of this group, nitrogen and phosphorus, are non-metals, and the next two, arsenic and antimony, are metalloids, while bismuth is a typical metal. Next, let's look at the trends in melting and boiling points. The melting point increases from nitrogen to arsenic due to the gradual increase in atomic size. The very low melting point of nitrogen is due to its discrete diatomic molecules. On the other hand, the high melting point of arsenic is attributed to its giant layered structure, in which the layers are closely packed. However, although the atomic size increases from arsenic to antimony, there is a decrease in their melting points. Although antimony has a layered structure, it has a low melting point than arsenic because of the relatively loose packing of atoms. Furthermore, the melting point of bismuth is less than antimony due to the loose packing of atoms by metallic bonding. On the other hand, the boiling point gradually increases from nitrogen to antimony, as shown in the table here. Next, let's look at the trend in the density of group 15 elements. The density of these elements increases regularly from nitrogen to bismuth. Finally, let's look at allotropy. All the elements in group 15, except for bismuth, show allotropy. Nitrogen exists in two allotropic forms, that is, alpha nitrogen and beta nitrogen. Phosphorus exists in many allotropic forms. Of these, the two important allotropic forms are white phosphorus and red phosphorus. Arsenic exists in three important allotropic forms: yellow, grey, and black. Antimony also has three important allotropic forms, namely yellow, explosive, and metallic. Let's now discuss the oxidation states of group 15 elements. Let us begin with negative oxidation states. You know that all the elements of group 15 have 5 electrons in their outermost orbit. Hence, they need only 3 electrons to complete their octet and attain noble gas configuration. The octet can be achieved either by gaining 3 electrons or by sharing 3 electrons by means of covalent bonds. As a result, the common negative oxidation state of these elements is -3. However, as we move down the group, the tendency to exhibit -3 oxidation state decreases. This is due to the increase in atomic size and metallic character. Only nitrogen atoms can gain 3 electrons from highly electropositive metals like lithium, and magnesium to form ionic nitrides. Note that a huge amount of energy, about 2125 kilojoules per mole, is required to form a nitride ion, that is, a N-3 ion. In spite of the huge amount of energy required, electron gain takes place in nitrogen because it is the smallest and the most electronegative atom. In other words, the nitrides formed are stable because the 3 electrons gained by the nitrogen atom are much closer to the nucleus. Examples of nitrides include lithium nitride, magnesium nitride, and calcium nitride. Compounds such as sodium phosphide and sodium bismuthide are also known, but these are not ionic. Nitrogen and the remaining elements of this group form covalent bonds and show a formal oxidation state of -3. For example, calcium phosphide and hydrides such as ammonia, phosphine and arsine. Owing to the gradual decrease in their electronegativity and ionization enthalpy, we can conclude that the tendency of these elements to show -3 oxidation state decreases down the group from nitrogen to bismuth. Nitrogen also shows -2 oxidation state and -1 oxidation state. -2 oxidation state is observed in hydrazine, while -1 oxidation state is observed in hydroxylamine. Apart from negative oxidation state, group 15 elements also show positive oxidation states of +3 and +5 by forming covalent bonds. However, due to the inert pair effect, or the tendency of a pair of s electrons to remain inert, the stability of +5 oxidation state decreases down the group, while that of +3 oxidation state increases. Note that bismuth pentafluoride is the only stable compound of bismuth known in its +5 oxidation state. You know that nitrogen is an element of the second period. Therefore, it has only s and p orbitals, but no d orbitals in its valence shell. Therefore, nitrogen can show a maximum covalency of 4 as there are only 4 orbitals available for bonding. A covalency of 4 is obtained by sharing its lone pair of electron with another atom of a molecule or ion. Therefore, nitrogen cannot exhibit a covalency of more than 4. For the same reason, it doesn't form pentahalides like NCl5 or NF5. However, phosphorus and the remaining elements can exhibit a covalency of 5 and a maximum covalency, also called expanded covalency, of 6. This is possible because of the presence of vacant d orbitals in the valence shell. The compounds of phosphorus and the remaining elements that show a covalency of 5 and 6 are listed in the table here. All the compounds of group 15 elements, which exhibit a +5 oxidation state, are covalent. However, in case of +3 oxidation state, both ionic and covalent compounds are formed. For example, bismuth trifluoride and antimony trifluoride are examples of ionic compounds. Similarly, nitrogen trichloride, phosphorus trichloride, and arsenic trichloride are examples of covalent compounds. In other words, the ionic character increases from nitrogen to bismuth due to the increase in the metallic character of group 15 elements. We can thus conclude that in group 15 elements, the covalent character decreases from nitrogen to bismuth. Talking again about nitrogen, because of its smaller size, high electronegativity and strong tendency to form p-pi multiple bonds, it exhibits various oxidation states from -3 to +5. Let us look at the wide range of oxidation states of nitrogen in its compounds. Nitrogen has an oxidation state of -3 in ammonia, -2 in hydrazine, -1 in hydroxylamine, 0 in dinitrogen, +1 in nitrous oxide, +2 in nitric oxide, +3 in nitrogen trioxide, +4 in nitrogen tetroxide, and +5 in nitrogen pentoxide. In case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. You know that a reaction in which the same element undergoes both oxidation and reduction is called disproportionation. For example, nitrous acid tends to disproportionate into nitric oxide and nitric acid, as shown in the equation here. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3, both in alkali and acid. For example, phosphorus acid tends to disproportionate into phosphoric acid and phosphine, as shown in the equation here. You know that generally, the first element of any group differs from the rest of the elements with respect to their properties. The same anomaly is reflected in group 15 elements. The first element in the group, nitrogen, differs from the rest of the elements in its properties. The unique properties of nitrogen are attributed to its small atomic size, high electronegativity or high ionization enthalpy, the non-availability of d orbitals, and the propensity to form multiple bonds. Only nitrogen can form nitride ions by gaining electrons due to its small size and high electronegativity. For example, lithium nitride and magnesium nitride. Nitrogen, being smaller in size, can effectively form p-pi bonds with other atoms of itself and atoms of other elements with a small size and high electronegativity, such as oxygen and carbon. The other elements do not form p-pi bonds because of their relatively larger size. In other words, the p orbitals of these elements are larger in size and, therefore, sideways overlapping will not be effective. The tendency of nitrogen to form p-pi bonds is one of the major features that distinguishes it from phosphorus and other group 15 elements. As nitrogen can form strong p-pi multiple bonds, it exists as a diatomic molecule with a triple bond between the two atoms. You know that this diatomic molecule is dinitrogen. The bond enthalpy of a triple bond being very high, about 941.4 kilojoules per mole. Dinitrogen is inert at ordinary conditions. For the same reason, it forms several compounds, such as nitrates, nitrites, azo and diazo compounds, oxides, oxoacids and cyanides. You know that in these compounds, nitrogen shows varied oxidation states. On the other hand, the other elements in the group, such as phosphorus, arsenic, and antimony, exist as tetraatomic molecules, as represented here. In all these molecules, only single bonds are present between the atoms. Note that bismuth forms metallic bonds in its elemental state. The catenation tendency is less for nitrogen when compared to the other elements of the group. This is because the single bond between nitrogen atoms is much weaker owing to the higher inter-electronic repulsions between the lone pair of electrons present on the nitrogen atoms. The high inter-electronic repulsions in dinitrogen are attributed to its smaller bond length or small size of nitrogen atoms. The maximum length of the chain observed for nitrogen is 3 in azide ion. Nitrogen doesn't form d-pi, p-pi bonds due to the absence of d orbitals. By contrast, heavier elements like phosphorus can form d-pi, p-pi bonds as seen in phosphorus oxochloride and triethyl phosphate as shown here. For the same reason, that is, due to the absence of d orbitals in nitrogen, it cannot form d-pi bonds. Due to the availability of vacant d orbitals in the remaining elements of group 15, compounds of these elements, such as triethylphosphine and triphenylarsine, form d-pi bonds with transition elements. Vacant d orbitals present in the phosphorus and arsenic of triethylphosphine and triphenylarsine accept electron density from filled transition metal d orbitals and form d-pi bonds as shown here. Let us look at the trend in the chemical reactivity of group 15 elements towards hydrogen, oxygen, halogens and metals. Let us begin with their reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3, where E can be nitrogen, phosphorus, arsenic, antimony or bismuth. They are named as ammonia, phosphine, arsine, stibine and bismuthine. Let us now study the gradation in chemical reactivity of these hydrides with respect to stability, reducing power, basic character and boiling and melting points. The table here shows that the bond dissociation enthalpy of hydrides decreases on descending the group, which further indicates that the stability of hydrides decreases from ammonia to bismuthine. This is because the central atom E increases in size down the group. With the increase in the size of the central atom, the EH bond becomes weaker. In other words, with the increase in size, the overlapping between the orbitals of E and hydrogen will not be effective. This accounts for the decrease in the stability of hydrides as we move down the group. Hydrides of group 15 elements are strong reducing agents. The reducing character of hydrides increases from ammonia to bismuthine due to a decrease in the strength of the EH bond down the group. Hence, bismuthine is the strongest reducing agent among all the hydrides of group 15 elements. These hydrides are basic in nature. They act as Lewis bases due to the availability of a lone pair of electrons on the central atom. However, their basic character decreases down the group with an increase in the size of the central atom. With the increase in size, the lone pair of electrons gets dispersed over a large area of the central atom. Thus, the tendency to donate the lone pair of electrons gradually decreases. The decreasing order of the basic nature of hydrides is represented here. It is apparent that ammonia is the strongest base of all hydrides. As you can see from the graph, the boiling point of hydrides decreases from ammonia to phosphine and then increases from phosphine to bismuthine. Note that there is a sharp decrease in the boiling point as we move from ammonia to phosphine. How do you account for this? It is because of the presence of intermolecular hydrogen bonding in case of ammonia. In other words, as ammonia molecules are associated through hydrogen bonding in liquid state, it has a higher boiling point than phosphine. Further, as we move down the group from phosphine to bismuthine, the increase in boiling point is attributed to the increase in their molecular weights. Note that the same trend is observed for their melting points. Next, Let's take a look at reactivity towards oxygen. Group 15 elements form two types of oxides, that is, E2O3 and E2O5. You know that nitrogen shows a strong tendency to form p-pi bonds with oxygen. As a consequence, nitrogen forms a wide range of oxides. Nitrogen forms 5 stable oxides, as shown here, exhibiting oxidation states ranging from +1 to +5, while the other elements form oxides only in +3 and +5 oxidation states. Bismuth can't form oxides in +5 oxidation state because of the inert pair effect. The lower oxides of nitrogen, such as nitrous oxide and nitric oxide, are neutral, while the higher oxides, such as dinitrogen trioxide, dinitrogen tetroxide, and dinitrogen pentoxide, are acidic. Oxides in the higher oxidation state of an element are more acidic than that of the lower oxidation state. Hence, the acidic strength of oxides of nitrogen increases from dinitrogen trioxide to dinitrogen pentoxide. As we move down the group, the acidic character decreases. In other words, the basic character of oxides increases on moving down the group. The oxides of nitrogen and phosphorus of type E2O3 and E2O5 are acidic, whereas the oxides of the type E2O3 of arsenic and antimony are amphoteric, and those of bismuth are wholly basic. Now let's look at reactivity towards halogens. All the elements of group 15 form trihalides and pentahalides with the general formula EX3 and EX5. Here, E may be nitrogen, phosphorus, arsenic, antimony or bismuth, while X may be fluorine, chlorine, bromine or iodine. For example, NF3, PF3, ASF3, SBF3 and BIF3 are trihalides. All the trihalides of these elements, except those of nitrogen, are stable. In case of nitrogen, only nitrogen trifluoride is stable. Nitrogen trichloride, nitrogen tribromide, and nitrogen triodide are unstable due to the large difference in the size of the nitrogen and halogen atoms, which weakens the nitrogen-halogen bond. Phosphorus, arsenic, and antimony form pentahalides due to the presence of vacant d orbitals in their valence shells. Nitrogen does not form pentahalides due to the absence of a d orbital in its valence shell. Pentahalides are more covalent than the corresponding trihalides. Moreover, the covalent character of halides decreases from nitrogen to bismuth. Note that bismuth trifluoride is not a covalent compound. All the elements of group 15 react with metals to form their binary compounds, showing -3 oxidation state, with the general formula M3E2. Here, M stands for metals such as calcium, magnesium, or zinc, while E stands for an element of group 15. For example, calcium nitride, calcium phosphide, zinc antimonide, and magnesium bismuthide. You already know that dinitrogen is abundantly available in the Earth's atmosphere and accounts for 78% by volume of it. Hence, dinitrogen is mainly obtained by the fractional distillation of liquid air. It is also the commercial method to prepare dinitrogen. The process of obtaining dinitrogen from air involves 2 stages. In the first stage, air is subjected to liquefaction. During liquefaction, a high pressure of 100 to 200 atmospheres is applied over dry air, followed by expansion through a fine jet. This process is repeated several times to obtain liquid air. In the second stage, the liquid air is subjected to fractional distillation. As dinitrogen has a lower boiling point, 77.2 Kelvin, than liquid oxygen, 90 Kelvin, it distills off first, leaving behind liquid oxygen. Thus, in this stage, dinitrogen is isolated from liquid air. In the laboratory, dinitrogen is generally prepared by gently heating equimolar aqueous solutions of ammonium chloride and sodium nitrite. Ammonium chloride and sodium nitrite react to form ammonium nitrite, initially as shown in the equation here. The ammonium nitrite so formed immediately undergoes decomposition to liberate dinitrogen gas. Dinitrogen can also be obtained by thermal decomposition of ammonium dichromate. The chemical equation corresponding to this reaction is shown here. Sodium azide or barium azide, when heated carefully to about 573 Kelvin, undergoes thermal decomposition to produce dinitrogen. The dinitrogen so produced is very pure. Have you ever heard this? Thermal decomposition of sodium azide, which generates dinitrogen, is used to inflate or fill airbags used as safety devices in some cars. Let us now look at some important physical properties of dinitrogen. Dinitrogen is a colorless, odorless, and tasteless non-toxic gas. Its vapor density is 14. Hence, it is slightly lighter than air. It can be condensed to a colorless liquid that boils at 77.2 Kelvin and can be solidified under high pressure to a white snow-like mass that melts at 63 Kelvin. It is diamagnetic in nature. It is slightly soluble in water. The solubility of dinitrogen at 273 Kelvin and 1 bar pressure is found to be 23.2 milliliter per 1 liter of water. It is important for us to study the reactivity of dinitrogen, as many of its applications are attributed to its reactivity. A molecule of dinitrogen consists of a triple bond that has a very high bond dissociation energy of 945.4 kilojoules per mole. Hence, dinitrogen is inert at room temperature. In other words, it is chemically inactive at room temperature, with the exception that it reacts with finely divided lithium to form lithium nitride. The reactivity of dinitrogen with lithium at room temperature is attributed to the highly active lithium. However, the reactivity of dinitrogen increases at higher temperatures. At high temperatures, dinitrogen reacts with elements from group 2, 13 and 14. It also reacts with hydrogen, oxygen and certain transition elements. At high temperatures, dinitrogen reacts directly with metals such as magnesium, calcium and aluminium to form the respective nitrides. It also reacts with hydrogen at high temperature and pressure in the presence of a catalyst to form ammonia, as shown here. Dinitrogen and oxygen react in equal volumes at a very high temperature of 2000 Kelvin to form nitric oxide, as shown here. Dinitrogen has several important uses. Being inert in nature, it has many uses in industry and other walks of life. For example, it is widely used as an inert atmosphere in iron, steel, and other metallurgical industries. During the processing of steel and iron, dinitrogen prevents the formation of undesirable oxides. In metallurgical industries, it prevents the harmful effects of oxygen. It dilutes the activity of oxygen in natural processes such as combustion and respiration. It is used in the preservation of packaged food material. A large amount of dinitrogen is used in the preparation of ammonia by Haber's process. The ammonia thus prepared finds application in the manufacture of fertilizers. Dinitrogen is also used in the preparation of nitrolim, a mixture of calcium cyanamide and graphite, which is an important fertilizer. Liquid dinitrogen is used as a refrigerant to preserve biological material. It is also used in cryosurgery to remove warts and other skin lesions. Let us first look at various methods to prepare ammonia. Ammonia is found in traces in the atmosphere. The bacterial degradation of nitrogenous organic matter of plants and animals forms ammonia. The equation corresponding to the formation of ammonia from the decay of urea is shown here. In the laboratory, ammonia is generally prepared by heating an ammonium salt with a base such as caustic soda or slaked lime. Ammonium chloride, when heated with lime or caustic soda, evolves ammonia gas. the gas evolved is dried over quicklime. The dry ammonia gas is then collected by downward displacement of air. In place of ammonium chloride, ammonium sulfate can also be used, but not other salts such as ammonium nitrate or ammonium dichromate. This is because the anionic parts of the salts, nitrate and dichromate, oxidize ammonium ions to dinitrogen or nitrous oxide. On an industrial scale, ammonia is prepared by Haber's process. The constituents of ammonia, nitrogen and hydrogen combine in a ratio of 1:3 at high pressures and moderate temperatures to form ammonia. The reversible thermochemical equation corresponding to this reaction is shown here. From this equation, it is evident that the formation of the product is associated with fewer number of moles. In other words, the reaction proceeds in the forward direction with a remarkable decrease in volume. Also, it must be noted that the reaction is exothermic. Hence, in accordance with Le Chatelier's principle, high pressure and low temperature favors the better yield of ammonia. However, as the rate of reaction would be slow at lower temperatures, the reaction is carried out at an optimum temperature of about 700 Kelvin. Further, to accelerate the reaction, that is, to attain the equilibrium faster, a catalyst like iron oxide and a promoter such as alumina are used. Thus, a high pressure of 200 to 300 atmospheres, an optimum temperature about 700 Kelvin, and the catalyst iron oxide along with the promoter alumina are used to obtain better yields of ammonia. The flow chart of the manufacturer of ammonia is given here. Let us describe in short the process of manufacture of ammonia from the flow chart. Pure and dry nitrogen and hydrogen are mixed in a ratio of 1:3. This reaction mixture is compressed under high pressure of about 200 to 300 atmospheres in a compressor. Then, these compressed gases are let into a catalytic chamber that is fed with finely divided iron oxide with alumina at 700 Kelvin. Subsequently, the ammonia formed along with unreacted nitrogen and hydrogen gases are liquefied to obtain liquid ammonia. You know that the structural aspects of a molecule justify most of its properties. Now let us take a quick look at the structure of ammonia. You know that ammonia is a covalent molecule. The central atom in ammonia is nitrogen, which undergoes sp3 hybridization. Among the 4 electron pairs present in the 4 sp3 hybrid orbitals, one is a lone pair. On account of the presence of one lone pair, the geometry of the molecule is not regular but distorted. Thus, the molecule acquires trigonal pyramidal shape. As a consequence, the bond angle is also less than expected, that is, 107.8 degrees. Now let us turn to some important properties of ammonia. Ammonia is a colorless gas with a pungent smell. It boils at 239.7 Kelvin and freezes at 198.4 Kelvin. You know that ammonia is associated with hydrogen bonding in both its liquid state and solid state. Hence, this factor accounts for the high boiling point and high melting point, that what is expected from its molecular mass. Note that liquid ammonia has high heat of vaporization. For the same reason, ammonia is highly soluble in water. Can you think of this? 1,176 volumes of the gas can be dissolved in 1 volume of water at 273 Kelvin. The aqueous solution of ammonia is alkaline because it produces hydroxyl ions. Its ionization in water is represented here. However, the dissociation constant of ammonia Kb being very small, it is a weak base. You know that ammonia acts as a Lewis base as it has a tendency to donate its lone pair of electrons to a proton or other electron-deficient molecules. Owing to its basic character, it combines with acids to form ammonium salts. For example, when passed through a solution of hydrochloric acid, it forms ammonium chloride. An aqueous solution of ammonia precipitates hydroxides of metals from their aqueous salt solutions, such as ferric chloride and zinc sulfate, as shown here in equations 1 and 2. The ferric hydroxide formed in equation 1 subsequently gets hydrated to form a reddish-brown precipitate of hydrated ferric oxide. Talking once again about its tendency to act as a Lewis base, it forms complex compounds with transition metal ions such as copper, silver, and cadmium. An aqueous solution of ammonia combines with copper sulfate solution to form a deep blue color. The deep blue color is due to the formation of tetraamine complex. Similarly, the formation of a colorless diamine complex of silver ion is shown here. It forms complex compounds by donating its electron pair to the metal ions, thereby forming coordinate bonds. Thus, the formation of complexes finds application in qualitative analysis, by which these metal ions can be separated from other ions present in the given salt mixture. Let us now take a look at some uses of ammonia. Liquid ammonia is used as a refrigerant on account of its high heat of vaporization. It is used to manufacture fertilizers such as ammonium sulfate and ammonium phosphate. It is also used in the manufacture of certain industrially important chemicals such as nitric acid, baking soda, and washing soda. You know that nitrogen forms a number of oxides that exhibit a wide range of oxidation states. The names of various oxides of nitrogen, their formulae, and oxidation numbers are listed in the table here. Note the oxidation states of nitrogen in all the oxides. You can see that the lower oxides include nitrogen 1 oxide and nitrogen 2 oxide, while the higher oxides include nitrogen 3 oxide, nitrogen 4 oxide, and nitrogen 5 oxide. We will discuss the physical appearance, structure, and chemical nature of each oxide, besides the most convenient method to prepare them in the laboratory. Let's start with nitrogen 1 oxide. Nitrogen 1 oxide, also called dinitrogen oxide or nitrous oxide, is usually prepared by heating ammonium nitrate gently to 240 degrees Celsius. Nitrous oxide is a colorless gas that is fairly soluble in cold water and the least soluble in hot water. Nitrous oxide is called laughing gas. Do you know why? This is because it produces hysterical laughter when inhaled, even in small amounts. Talking about its chemical nature, nitrous oxide is a neutral oxide. Nitrous oxide is a linear molecule that is a resonance hybrid of the two forms shown here. The bond lengths in the molecule are 113 picometers and 119 picometers. Nitrogen 2 oxide, also called nitrogen monoxide or nitric oxide, is prepared by the reduction of nitrite salt with ferrous sulfate. In this method, an acidified ferrous sulfate solution is warmed with a concentrated solution of sodium nitrite to get a pure sample of nitric oxide. Nitric oxide is a colorless gas that attains blue color when liquefied. It is sparingly soluble in water. Just like nitrous oxide, it is also a neutral oxide. Note the structure of nitric oxide, which is a resonance hybrid of the two forms represented here. The bond length is 115 picometers, which is intermediate between double bond and triple bond. From the structure, it is evident that nitric oxide is paramagnetic in nature due to the presence of an unpaired electron. Nitrogen 3 oxide, also referred to as dinitrogen trioxide or nitrogen sesquioxide, is obtained as a blue liquid when a mixture of nitric oxide and nitrogen dioxide or dinitrogen tetraoxide is cooled to below -20 degrees Celsius. You can see from the equation that dinitrogen trioxide is anhydride of nitrous acid. Also, it is evident from the reaction of dinitrogen trioxide with an alkali that it is acidic in nature. Let us take a look at its planar structure, which is a resonance hybrid of these two forms. Note the different bond lengths and bond angles in the molecule. Nitrogen 4 oxide, also called nitrogen dioxide, is prepared by heating lead nitrate at about 673 Kelvin. Nitrogen dioxide is a brown gas that is a mixed anhydride of nitrous acid and nitric acid. It neutralizes alkalis to form nitrites and nitrates. Hence, it is an acidic oxide. Examine the resonance structures of nitrogen dioxide. The molecule exists as a resonance hybrid of these structures. The molecule is angular in shape with a bond angle of 134 degrees and bond length of 120 picometers. Note the unpaired electron in the resonance structures of nitrogen dioxide, due to which it behaves as a paramagnetic substance. It is because of this reason that it attains a tendency to dimerize to a colorless dinitrogen tetroxide molecule that has an even number of electrons. At low temperatures, nitrogen dioxide associates to solid dinitrogen tetroxide. Take a look at the planar structure of dinitrogen tetroxide and make a note of the bond angles and the bond lengths in the molecule. These two oxides exist in equilibrium in a wide range of temperature, from -11.2 degrees Celsius to about 100 degrees Celsius. Below -11.2 degrees Celsius, only solid, colorless dinitrogen tetroxide exists, while above 140 degrees Celsius, only gaseous brown nitrogen dioxide exists. Nitrogen 5 oxide is also called dinitrogen pentoxide. It is prepared by the dehydration of nitric acid with phosphorus pentoxide. It is a colorless crystalline deliquescent solid that readily dissolves in water to give nitric acid. Hence, it is an anhydride of nitric acid. It neutralizes alkalis to give nitrates, as shown here. Thus, the oxide is acidic in nature. Here is the symmetrical resonance hybrid of these two structures. It is a planar molecule with two different bond angles and bond lengths as shown here. This symmetrical planar structure is observed only in its vapor state, which otherwise is ionic in the solid state. The ionic solid is referred to as nitronium nitrate. From the structure, try to answer this question on your own before looking at the solution. What is the covalence of nitrogen in dinitrogen pentoxide. From the resonance structures of dinitrogen pentoxide, it is evident that each nitrogen atom is bonded to 3 oxygen atoms by 4 covalent bonds. Hence, the covalence of nitrogen in dinitrogen pentoxide is 4. Nitrogen forms a number of oxo acids, such as hyponitrous acid, nitrous acid, pernitric acid, and nitric acid. Of these, nitric acid is an industrially important oxo acid. Let us first look at the various methods to prepare nitric acid. In the laboratory, nitric acid is prepared by heating potassium nitrate or sodium nitrate with concentrated sulfuric acid in a retort. The vapors obtained are condensed in a water-cooled receiver. On a commercial scale, it is prepared by Ostwald's process. The first step in this process is the catalytic oxidation of ammonia into nitric oxide. The nitric oxide is then oxidized to nitrogen dioxide, from which nitric acid is formed. Let us take a quick look at the process. First, a mixture of dry ammonia and air is passed through a catalytic chamber that is fed with preheated platinum gauze. The platinum gauze is preheated electrically to about 1155 Kelvin. It is a colorless liquid that boils at 84.1 degrees Celsius and freezes to a white solid at minus 41.55 degrees Celsius. Note that the specific gravity of laboratory-grade nitric acid, containing 68% by mass, is 1.504. In the laboratory, the nitric acid stored in bottles is usually yellow in color. Do you know why? Try to answer the question on your own before looking at the answer. Nitric acid undergoes photochemical dissociation to produce brown nitrogen dioxide gas. The brown nitrogen dioxide dissolves in the colorless nitric acid, turning it yellow. An aqueous solution of nitric acid undergoes ionization to produce hydronium ions and nitrate ions. On account of its ability to dissociate almost 100% to produce hydronium ions, it is considered a strong acid. On the other hand, the nitrate ions lend the acid solution its oxidizing property. Moreover, hot and concentrated nitric acid acts as a powerful oxidizing agent. You know that metals such as copper and zinc are insoluble in hydrochloric acid. However, these metals dissolve in nitric acid. The products formed depend on the concentration of the acid and the temperature. Concentrated nitric acid reacts with copper and zinc to give nitrogen dioxide. Dilute nitric acid reacts with copper to give nitric oxide and with zinc to give nitrous oxide. Certain metals such as chromium, aluminium and iron are rendered passive towards an attack by nitric acid. This is due to the formation of a thin layer of oxide on the surface of these metals. Noble metals, such as gold and platinum, are insoluble even in hot and concentrated nitric acid. However, these metals dissolve in a concentrated solution of nitric acid and hydrochloric acid taken in the ratio of 1:3. This solution is called aqua regia. Note that noble metals dissolve in aqua regia due to its ability to produce nascent chlorine. The nascent chlorine eventually forms a soluble complex on reacting with gold and hydrochloric acid, as shown in these equations. Concentrated nitric acid oxidizes nonmetals such as carbon, phosphorus, sulfur, and iodine to their corresponding higher oxo acids. The nascent oxygen produced from the dissociation of nitric acid oxidizes these nonmetals. You can see from the balanced equations that carbon is oxidized to carbonic acid, phosphorus to phosphoric acid, sulfur to sulfuric acid, and iodine to iodic acid. Let us now look at the familiar brown ring test. This test confirms the presence of nitrate ions in a given salt. Freshly prepared dilute ferrous sulfate is added to the aqueous solution of a nitrate. The test tube is then slanted slightly and concentrated sulfuric acid is added drop by drop, allowing it to slide along the sides of the test tube. A brown ring forms at the junction of the two layers. The brown ring confirms the presence of nitrate ions. You can see from the equation that the ferrous ion reduces nitrates to nitric oxide. The nitric oxide formed reacts with ferrous ions to form a brown complex. The brown color is due to the formation of a hydrated nitrosyl complex of iron. Let us now turn to the uses of nitric acid. Nitric acid is widely used in the manufacture of dyes and drugs, as well as explosives such as trinitrotoluene or TNT, nitroglycerine, and picric acid. The salts of nitric acid, such as ammonium nitrate and calcium nitrate, are used as important fertilizers. It is used in the purification of silver and gold. It is used in the laboratory as an oxidizing and nitrating reagent. It finds a major use in the pickling of stainless steel, etching of metals, and as an oxidizer in rocket fuels.